Welcome, ladies and gentlemen. My name is Basil Omari, and I will be going through my ECE 106 design project. Just a quick note before we start. You might see some text that is colored in green. That is simply the in-text citation for my references. So if you feel so inclined to read further about the given topic, I would definitely advise and encourage you to do so. I'll be leaving a full list of references at the end of the presentation. So in this design project, I've designed a capacitive water level sensor, and it measures the height or level of stored water inside of a water container tanker. As you can see in the diagram, the capacitive sensor is installed along the height of the tank, and it provides us with a continuous measurement of how full or empty our tank is. Now you might be asking, where does the capacitor come into play here? The sensor is actually based upon the concentric cylindrical capacitor. And as you can see in the diagram here, which represents or illustrates, our capacitor, we have our inner electrode or inner cylinder here, and our outer cylinder or outer electrode, both of which comprise the capacitor used in our sensor. And between these two cylinders, we have this gap here, which fills up with water. Now, this would typically be standing upright as opposed to laid down like this. And as water rises up through the tank, it would begin to fill up through this gap here between the two cylinders. Also, you might notice insulation layers here between the two electrodes, or like surrounding all the electrodes, and that's just to prevent charge from flowing through the water. Now, water flows in and out of the capacitor through a hole at the bottom of the sensor, and as it flows in, it occupies the space that was previously filled by air. And the difference in dielectric constant between air and water would lead to a change in capacitance as water flows in and out. Specifically, since water has a higher dielectric constant than air, then we expect the capacitance to increase as the water flows up the capacitor, and vice versa. The capacitor will be connected to a designated electric circuit, which helps us measure this change in capacitance, and that would be done by measuring the time constant. Nevertheless, I'll get more into details regarding the capacitance and the designated electric circuit later on in this presentation. Considering we are designing a real product here, there are significant practical implications that I must consider, and which I'll be going over right now. The first practical consideration is the fringe fields. These can be minimized through multiple ways. First off, they can be minimized by using a cylindrical capacitor as opposed to a parallel plate capacitor, as they usually provide a higher ratio of surface area to perimeter, and because fringing often occurs at the periphery of the capacitor. Additionally, research conducted by Valencia's Polytechnic University has shown that reducing the distance between the inner and outer cylinders of the capacitor would also help reduce the effect of fringing fields, which is what I have attempted to implement in my designs. That same research shows that for our selected dimensions of the capacitor, that is, length of 1 meter and distance of 0.02 meters between the cylinders of the capacitor, I'll go more into details about the dimensions later in the design section of the presentation. For those dimensions, the effect of fringe fields become very minimal, and thus we can simply neglect their presence and their effect. The next practical consideration is the conductivity of water. Now, the ionized water that is stored inside a tank, and which we will be attempting to measure the height of, is of course conductive, and this causes charge to flow between the cylinders of the capacitors, which we must attempt to reduce and minimize. I've attempted to minimize this in my design by wrapping both cylinders or electrodes of the capacitor with an insulating layer of PVC, which has a dielectric constant of 4.2, such that neither one of the electrodes or cylinders is ever directly exposed to water or is in contact with the water. This presence of the PVC layers will also be taken into consideration in the theoretical calculations of the design. The final practical consideration is the temperature of water. The common dielectric constant used for water, which we usually see in textbooks and on the internet, is 78.25, but that is in room temperature. And research has shown that dielectric constant is dependent on temperature. Now, the average outside temperature in my home country of Jordan during this spring season is 17 degrees Celsius. And at that given temperature, the dielectric constant used for water must be 82.1, which is what I'll be using in my theoretical calculations. Next, we'll be taking a look at the theoretical model, which estimates and shows how the capacitance changes as the height of the stored water changes in our given system. Before we get into that, I must briefly go over the assumptions that I have made when constructing the theoretical model. First of all, I have neglected fringing fields. As I have previously explained, their effect in our given system and for our given dimensions is very minimal, and thus I've chosen to neglect their presence. Second off, the volume of the cylindrical capacitor, which is not filled with water, I have assumed to be filled with air, which has a dielectric constant of 1.00059, but I'll be rounding that down or assuming it to be simply 1. Third of all, the water level, or like the rising water level, I have assumed to be perfectly horizontal, no angle or no uneven level in the water that is flowing up or flowing down in the capacitor. And finally, the capacitive sensor that I've been using is of the exact height of the tank, such that when it reads a height of 0, that means that the tank is completely empty. And when it reads its maximum height, that means that the tank is completely full. What you see here on the right is a simplified diagram of our sensor. It illustrates half of the perpendicular cut of the cross section of the capacitor. And X here represents the height of the water flowing through. L represents the length of the sensor and the water tank. A represents the radius of the inner cylinder. B represents the radius to the inner PVC layer surrounding the inner cylinder. C represents the radius to the inner PVC layer surrounding the outer cylinder. And D represents the radius to the outer cylinder or the outer electrode of the capacitor. And all measurements that you will be seeing for these lengths must be obviously in meters. Now, the calculations for the capacitance can be simplified if we simply reimagine our capacitor's layout. Essentially, we have 3 capacitors that are in series. C1 here and C3 represent 2 capacitors that correspond to the PVC insulation layers. And C2 here consists of 2 capacitors that are in parallel. The first is the capacitor which is filled with water that has a dielectric constant of 82.1, and the second is the capacitor that is filled with air, which has a dielectric constant of approximately 1. And finally, the unit for capacitance, which will be used throughout our calculations, is farads. The capacitance for a concentric cylinder capacitor is expressed by the following equation here. And using this equation, we can easily calculate the capacitance of the C1 capacitor and C3 capacitor corresponding to the PVC insulation layers, which are presented here. For the air-water layer, since we essentially have two capacitors in parallel, the total capacitance for this layer is the sum of the individual capacitances for both the air-filled and the water-filled capacitors. Notice that both these individual capacitances are dependent on the height of water, x, and as such, the total capacitance for this layer is also dependent on the height of the water, x. As we have mentioned, the three capacitors are in series, and as such, the reciprocal of the total capacitance is the sum of the reciprocal of all three capacitances. This is expressed in the following equations here. The diagram on the right presents the selected dimensions for our design of the capacitive sensor. By plugging in these dimensions into our previously formed equation, we produce a function for the capacitance in terms of x, or the height of the water. The following graph presents this relationship of the capacitance in farads as a function of the height of the water in meters. Notice that the capacitance increases as the height of water increases, but this increase slowly begins to plateau. Next, we will attempt to optimize the capacitor and capacitance to increase its sensitivity. The capacitance is dependent on the height of the water, x. Therefore, sensitivity would be the change in capacitance per meter change in the height of the water, and it would have units of farads per meters. It is derived by differentiating the capacitance with respect to the height of the water, x, which would produce the following equation. This relationship is plotted in the following graph, which illustrates the sensitivity measured in farads per meter as a function of the height of the water in meters. Notice as the height of the water increases, we see that the sensitivity begins to approach 0. From the previously specified equation for the sensitivity, no specific geometric variable displayed an obvious relation to the sensitivity. I tested the effect of changing both the radius of the inner insulation layer, represented by B, and the effect of changing the dielectric constant on the value of the sensitivity. And this was done by making all other variables constant and solely changing either the radius of the insulation layer or the dielectric constant value. The following graphs display this relationship. The following graph presents the sensitivity measured in farads per meter with the change of a radius b in meters. We see that for the valid values of b, that is between 0.015 meters and 0.03 meters, a decrease in the value of b corresponds to an increase in the value of the sensitivity. We conclude that we must opt for the smallest feasible value of b to increase sensitivity. I have selected the value of b equals 0.018 meters, which provides a PVC plastic layer of 0.003 meters thick around the inner cylinder or inner electrode. This provides a perfect balance between high sensitivity and thickness of PVC layer, which we can realistically build and design. The following graph presents the value of sensitivity, which is also measured in farads per meters, with respect to change in the dielectric constant value of the insulator. Notice that as the dielectric constant is increased, we observe an increase in the sensitivity. Therefore, we conclude that we must opt for an insulator of high dielectric constant. I've converted from using PVC to using rubber, which is also a very good insulator and has a higher dielectric constant of 7 as opposed to the dielectric constant of PVC, which is 4.2. The following graphs provide the new values of the capacitance and sensitivity with respect to height of water after our new optimizations and implemented changes. Notice that the overall values for the sensitivity are much higher than they were prior to the implemented changes. Next, I will go over the designed electric circuit used to measure the capacitance for our system. To measure the capacitance, the following DC resistor capacitor circuit was designed. I have incorporated a 5 mega ohms resistor, a 50 volt voltage source, and have connected it to an oscilloscope. Two main considerations must be brought up. Number one, the positive terminal will be connected to the inner cylinder of the capacitor, and the negative terminal will be connected to the outer cylinder or the outer electrode of the capacitor. Second consideration is that the oscilloscope will be used to measure the time constant, which is then used to derive the capacitance of the cylindrical capacitor. Now, what is the time constant? The time constant, denoted by tau, represents the time required for the voltage of the capacitor to reach 63.2% closer to the voltage source, Vs, connected to it. It can be measured in an oscilloscope by measuring the time difference for the voltage of the charging capacitor to increase by 63.2% closer towards Vs. This time difference represents the time constant. To derive an equation relating the time constant, which has a unit of seconds, to the capacitance, which is in farads, we look at the equation expressing the voltage of the capacitor as a function of time, which is the first equation. As defined, the time constant, or tau, is the time at which we reach 63.2% closer to the source voltage. Thus, if we assume that the capacitor is fully discharged at first, i.e. voltage equals 0, when time t equals tau, or the time constant, we have that the voltage reached by the capacitor equals to 0.632 of the voltage source, as expressed by the second equation. Rewriting this equation, we have that the time constant is equal to the resistance of the resistor in the RC circuit multiplied by the capacitance of our capacitor. To derive the sensitivity in terms of time constant change versus capacitance change, we differentiate with respect to the capacitance to produce the following, the final equation, where R is expressed in ohms. Finally, we take a look at the overall sensitivity of the arrangement, which is the change in time constant, which has a unit of seconds, as the height of the water, measured in meters, changes. We have that the time constant is the product of the capacitance and the resistance. We substitute the value of the capacitance in terms of x, the height of the water, from our theoretical model to produce the following equation, which is the time constant as a function of the height of the water. We differentiate with respect to x, or the height of the water level, to obtain the overall sensitivity of the arrangement. The first graph on the left illustrates the relationship between the time constant in seconds and the height of the water in meters. And the second graph on the right illustrates the relationship between the overall sensitivity of the system which is in seconds per meters, and the height of the water, which is in meters. Notice that for the time constant, it increases as the height of water increases, and once again we see a plateau in that increase. And for the sensitivity, it decreases as the height of the water increases. Considering we use an oscilloscope of a sample rate of 20 megahertz, the smallest difference in time that we can measure is 5 times 10 to the power of negative 8 seconds. We rewrite the equation of the overall sensitivity to evaluate the detection limit, or the smallest change in the height of water that we can measure. That is expressed by the following equation. By substituting in our numerical values, that is, the dimensions of the capacitor and the smallest difference in time constant, we have that the detection limit is dependent on the height of the water, which is measured in meters, and it is expressed by the following equation. We must finally note that the detection limit also has unit of meters. The following is the graph representing the detection limit as a function of the height of water. Notice that as the height of the water increases, we see that the detection limit also increases. Thank you very much for watching. The following is just the list of references.